Hey guys, today we're going over the midpoint rule to approximate the area between two curves. I would like to quickly point out that GeoGebra already has a command called rectangle sum that you can use to obtain midpoint approximations of definite integrals of a single function. However, as far as I know, I don't think there's a command in GeoGebra to calculate midpoint approximations for the area between two curves. So we're going to build this from scratch. Okay, so let's get started. Alright, so we're going to start by typing our two functions. Our first function is going to be y sub t of x equals 2x minus x squared. Our other function is y sub b of x equals x squared. And let's go ahead and zoom in by using the scroll wheel. And let's reposition this. And if you want to turn off the grid, you can right click, select show grid and no grid. Next, let's determine the points of intersection. So let's type in intersect, press enter, and let's go with the first option. We'll provide our two functions here, so we'll do y sub t and then y sub b. And here we see that the two functions intersect at the origin and at the point 1, 1. We will also need a slider, so I'm going to call the slider n, and let's type in slider. And I'm going to have this go from 1 to 100 using increments of 1. The next step is to partition the closed interval 0, 1, and we will accomplish this using the sequence command. As you probably already learned in calculus, first we're going to partition a closed interval AB into n closed subintervals of equal length delta x, which we calculate in the usual way by subtracting a from b and dividing that difference by n. Note that the partition I'm using here is different from what you might see in your calculus textbook. And the reason why I'm doing it this way is because in GeoGebra, list indexing begins at 1. Once we have our x of i's, we can then get our midpoints for each subinterval by averaging the endpoints of each subinterval. Here we'll denote the midpoint using x-bar notation. Alright, so let's go back to GeoGebra. As I said earlier, we're going to use the sequence command to create our partition. I'm going to create a list and call it xvals. Let's type in sequence, press enter, and we'll go with the third option. Okay, so my starting value is going to be the x coordinate of point A, so we'll type x of A. Then for the ending value, that will be x of B. And our increment is going to be delta x, so we'll type x of B minus x of A. That's going to be divided by n, which is the number of subintervals or the number of rectangles that we're going to use in our animation. So let's press enter. And let me go ahead and expand this a bit more. Now let's go ahead and increase n to, let's say, n equals 5. And let's verify that what we did is correct. So we can do that by typing xvals and then 0, and it plots the points along the interval from 0 to 1. And that looks good. What I want to do next is get the midpoints for each subinterval. So again, we're going to use the sequence command. I'm going to call this xmid. Let's type in sequence. And this time we're going to go with the last template. For our expression, we're going to take the average of the endpoints of each subinterval. So we'll type xvals of I plus xvals of I plus 1 divided by 2. Our index variable is going to be I. Our starting value is going to be 1. The ending value is n, and let's go ahead and use an increment of 1. Oops, I made a mistake. Let me fix that really quickly. So we'll type in I, 1, and an increment of 1. Okay, so again, let's go ahead and verify to see if we did this correctly. So we'll do xmid, then 0. It's kind of hard to see. Let's go ahead and select a different color for this. So let's go with something that stands out a bit more. Alright, so that looks good. Let's go ahead and evaluate our top function at the midpoints first. So we'll type y sub t evaluated at the midpoints. Okay, and that returns a list. And let me call this list, let's see, y val of t. And we'll do the same for the other function. So we'll type y val of b and evaluate y sub b at the midpoints. Press enter. Now that we have a partition and the values of both functions evaluated at the midpoints of each subinterval, we can create a sequence of rectangles using the polygon command. The polygon command simply requires a list of points, and for us, that's going to be the 4 vertices of the ith rectangle. Alright, so let's go ahead and create our sequence of rectangles. Before I do that, let me expand this a bit more. I'll reposition this, make it a little bit bigger, and I don't think I need these points down here, so let me turn those off. I'm going to call this list mid-rect. Let's type in sequence, press enter, and we'll go with the last option here. Our expression is going to be the polygon command along with the 4 vertices of the ith rectangle. We'll start with the point located at the bottom left corner and go clockwise from there to form the rectangle. I'm going to type in the entire command, then we'll go ahead and take a look at it carefully. Okay, so I just finished typing in the command and it looks like it worked. Let me expand this a little bit more so we can take a look at this command in more detail. Okay, so let's go ahead and take a look at our first point. X-vals of I is simply x of I. Y-val b of I is the bottom function evaluated at the midpoint. The second point corresponds to the point located at the top left corner. Again, x-vals of I is x of I. Y-val t of I is the top function evaluated at the midpoint. For the last 2 points, it'll be something similar. The only difference is that the x-coordinate of the points will be x of I plus 1, which we represent with x-vals of I plus 1. Notice that GeoGebra returned a list of values. What do these values represent? Well, they represent the areas of each of the rectangles. So if we take the sum of these values, what we'll get is the sums of areas of the approximating rectangles. So let's go ahead and type in sum, and what we want to sum is the list mid-rect. Press enter, and we get an approximation of 0.34. I'm going to call this mid-sum. Now, how does this approximation compare to the area between the 2 curves? Well, as you probably already know, we obtain better estimates of the area between the 2 curves by increasing the number of rectangles. Before we run our animation, let's find the area between the 2 curves by using the integral between command. So let's type that. Integral, and it's already there. Select it, press enter, and let's go with the first option. And here we'll provide our 2 functions, so that's y sub t. Then y sub b for the second parameter. Our starting value will be the x-coordinate of point A, which we already know is 0. The ending value will be x of b. Let's press enter. Let's turn this off, and you see that GeoGebra already shaded the area between the 2 curves, and we also have an approximation here. Okay, so let's go ahead and turn on our rectangles again. And let's go ahead and start our animation. So we'll type start animation, press enter. And here we'll provide the slider name, which we called it n earlier, so let's do that and press enter. And you see that as we increase the number of rectangles, the approximation gets better and better, and it approaches the actual area here. Okay, so let's turn this off. Let's go ahead and bring this down again. Let's see how good our approximation is. So I'm going to call this error. And we'll use the absolute value, press enter, and we'll take A, then subtract the mid-sum, press enter. Let's run our animation again, so we'll type start animation, first option, and let's provide the slider name n. Let's run it again. And you can see that our error gets smaller and smaller with increasing number of rectangles. Great. Let's stop this. With the techniques that I showed you today, instead of using midpoints, try using left and right endpoints for the rectangles to approximate the area between the 2 curves. That should do it for today. Thanks for watching and see you next time.